Hi everyone, in this video we're going to introduce the concept of partial fractions. To motivate this topic, let's suppose you wanted to calculate this antiderivative. Now, the hard thing about antiderivatives is that there's no recipe that's always going to get the job done. Sometimes we just have to try things and hope that they work, and if they don't, we go back and try something else. But it's also important to gain some awareness of what things would typically work well or not so well, so that we're not completely shooting in the dark. We've seen, for example, that forming a common denominator can be a good idea, at least when working under a square root. But what about a situation like this where there isn't a square root? Is a common denominator still a good idea? Well, the only way to find out is to try it. And this is what you would end up with. At this stage, some students might also have a temptation to expand everything out on the top and the bottom. Is that a good idea? Well, again, the only way to find out is try. So pause and check that you'd get these results if you did that. And now that we've actually done all this, we can come back to the question of whether or not this led us somewhere useful. Was this a good idea or not? And to address that, let's make a comparison. Pause here and decide whether you think taking these steps made it easier or harder to calculate this integral. I'm about to spoil it, so make sure you're ready to continue. I hope that you answered that in doing all this, we actually made the integral harder. And that's because the integral we started with was actually pretty easy to begin with, just by applying our antiderivative to each term separately. The second term there would need a u substitution, but the details of that would work out pretty nicely. And so on the whole, I'd say this integral is easy to calculate if you approach it this way. On the other hand, if we'd gone ahead and formed that common denominator, it would have been much harder to see what should be done next. So coming back to the question of whether getting a common denominator was a good idea, I would say that the answer is no. When it comes to simplifying, it's important to recognize that just because you can doesn't mean you should. And what's considered simple depends on what you're trying to do. So anytime you're making simplifications, I suggest trying to identify a specific reason why that simplification might actually help you. Because if you can't think of a reason, then you might be wasting your time or even leading yourself in an even more difficult direction. Now, we've just seen that common denominators can make integrals harder. But that also means undoing a common denominator could make an integral easier if we had a way to do that. So that actually gives us a reason to try to have a method for reversing the process of forming a common denominator. And it turns out there actually is a method for that. It's called partial fractions. So let's start with the definition of what is a partial fraction. A partial fraction is a fraction with one of the following forms: a constant over a linear function, or a linear function over an irreducible quadratic. But actually, we also allow for the denominator to be raised to a power, which I'll call k, as long as that power represents a positive whole number. So let's look at some examples of partial fractions, starting with this first type. Remember that a linear function is something of the form mx plus b, and so this fraction would be an example of something matching this form of constant over linear to the power of k, where in this case k is 4. Here's another example, although considering the way this is written, you might wonder if this really matches the definition, since it seems like there's no power here. But there's technically an exponent of 1 even when we don't write it down, so this does still count as a partial fraction where k is equal to 1. Here's an example of the second type. The numerator here is just x, which is a linear function, and the denominator is a quadratic function raised to the power of 3. But to be confident that this really matches the definition, we need to verify that this quadratic is irreducible, or in other words, not factorable. That's what irreducible means. That can be done by calculating this b squared minus 4ac from the quadratic formula. This quantity is called the discriminant, in case you need a reminder of that. In this case, the discriminant gives us a negative value, meaning the quadratic formula would have us taking the square root of a negative number. And when that happens, we know our quadratic function can't be factored, or in other words, it's irreducible. So that confirms that this fraction does match the definition after all. Here's another example of a partial fraction of this second type. The only difference actually between this and the first example is that I put a 2 in the numerator instead of an x. And you might wonder, does that really match the definition still? Because, is 2 really a linear function? And the answer to that is yes. Importantly, a linear function can be a constant because after all, the function y equals 2 still represents a straight line. So let's go through several examples and decide which of these matches the definition of a partial fraction and which ones don't. Pause here and come up with an answer and a reason for each of these about whether or not these are partial fractions. And when you're ready to be spoiled, let's look at the answers. This first one is not a partial fraction because this is of the form linear over linear, not constant over linear. So it doesn't match either of the given types. This second one is also not a partial fraction because although it is linear over quadratic, the denominator can be factored, so it's not an irreducible quadratic in the denominator. This next example is a partial fraction, although this is a bit tricky because the denominator doesn't appear to be made from a linear or a quadratic function, so it wouldn't at least immediately seem to match the definition I gave you. But actually, if we factor the denominator, we can see that it is the square of an irreducible quadratic. Pause if necessary to convince yourself of this factoring, and be aware that sometimes you might need to factor before you can recognize something as a partial fraction. And this last example is a partial fraction of type constant over linear squared. Be careful not to classify this one as linear over irreducible quadratic. The denominator here is quadratic, but it's also reducible because it can factor as x times x. So constant over linear squared is the correct way to think about this one as opposed to linear over irreducible quadratic. So here's the reason why this definition I gave you is important. It turns out that every proper rational function can be written as a sum of partial fractions. So let's break down the meaning of this statement. A rational function is something of the form polynomial over polynomial. But what do I mean by proper rational function? Well, that means that the degree of the numerator is smaller than the degree of the denominator. And remember that degree just means the highest power of x that appears in the polynomial. Let's see if we can apply this fact to the rational function we were looking at in the beginning of the video. First, note that this is proper because the numerator and denominator have degree 3 and 5 respectively. And we also saw that this expression came from forming a common denominator among these two terms. That is the example we looked at the very beginning of this video. And if you look at each of those two terms carefully, you'll see each of those matches the definition of a partial fraction. So this equality actually tells us that our proper rational function on the left is equal to the sum of partial fractions on the right. And that's exactly what the fact tells us that we should be able to do. This sum of partial fractions is what we call the partial fractions decomposition of our rational function. That's pretty cumbersome to say though, so it's fine with me if you abbreviate this as PFD in the future. Now, why is partial fractions decomposition important? Well, that's because coming up with this decomposition literally represents the process of undoing that common denominator. The fact here is telling us that it's always possible to achieve this, which is a good thing because it makes finding antiderivatives easier, as we saw before. But there's still this question of how do we achieve it? How do we come up with the partial fractions? With the example I showed you here, we were only able to achieve it because I literally gave us these partial fractions at the beginning of the video. If I hadn't done that, how would we come up with these partial fractions? Well, I'll save that for the next video, so look forward to that, and I'll see you next time.